Okay. Hey guys, I'm going to go ahead and run through some notes for 10.1. This is what I had wanted to do after school yesterday, but it's fine. I'm not at all hurt that nobody showed up. Okay, so anyways, we have our objectives for 10.1 here. I'm going to try and send a PDF of this before I send out this video. Hopefully you're able to print it. If not, you can kind of follow along and it should still be able to help. So sampling distributions for the difference of two proportions. Remember that we already went through this section. I'm just doing some extra notes, so a lot of this you will have heard before. Actually, all of it you should have heard before, just you might not remember it since we weren't really writing stuff down. Okay, so for the sampling distribution of the difference between two proportions, that just means all possible values of p hat 1 minus p hat 2 and how often they occur. This is a sampling distribution, so remember that just means that we're taking a ton of samples of the same size, calculate the p-hats for each, and then we make a distribution that's just all the p-hats from all the different samples. Right, so if I took many different samples and found the p-hats for each, that would be my sampling distribution. So the sampling distribution for p hat 1 minus p hat 2 is just the differences for two different groups of that. Okay. What are the shape, center, and spread of the sampling distribution of p hat 1 minus p hat 2? If you remember, we're pretty much just going to say normal or approximately normal or not approximately normal. And so we're going to say that it is approximately normal if, anybody know? Okay, you can't answer me, but hopefully you do know. It's N1P1 greater than or equal to 10, and, oh, dang it. Just like in class. Okay. N1, 1 minus P1 greater than or equal to 10, and 2P2 greater than or equal to 10, and 1 minus P2 greater than or equal to 10. All those things have to be true, and if they are, then we can see that the shape of the sampling distribution of the difference in the sample proportions is approximately normal. Okay, what else do we want to talk about? Center. That's the easy one. We're going to talk about the mean. Remember that we have other measures of center. We've just been using mean for a while now. And we're going to say that mu p hat 1 minus p hat 2 is equal to, if we knew the population proportion of p hat 1, or sorry, p1 minus p2. Okay. For spread, we're going to look at standard deviation. And our formula for that, I'm just going to write SD for standard deviation, is sigma p hat 1 minus p hat 2. And that should be equal to remember that this was the standard deviation of the sampling distribution when we only had one sample and we were just looking at one population, so we didn't put those little ones on there, but that was it before. And now it's very similar. It's just we add together the variances and then take the square root after that to get the standard deviation. But we can only say that if we meet the conditions for random and 10%. Okay. All right. So an example. Nathan and Kyle both work for the Department of Motor Vehicles, but they live in different states. Super interesting. In Nathan's state, 80% of the registered cars, 80% of the registered cars are made by American manufacturers. It's probably going to be a P of sorts. In Kyle's state, only 60% of the registered cars are made by American manufacturers. Nathan selects a random sample of 100 cars. That sounds like an N. And Kyle selects a random sample of 70 cars. That's probably the other N, huh? Okay, so let P hat N minus P hat K, N and K, of course, being for Nathan and Kyle, be the difference in the sample proportion of cars made by American manufacturers. What's the shape of the sampling distribution of P hat N minus P hat K? Why? Okay, well, we know that the shape is going to be approximately normal as long as we met these conditions for large counts that we named above. So let's go ahead and check those counts. So for Nathan took a random sample of 100 cars. And the proportion of registered blah, 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 American manufacturers in his state was 0.8, or 80%. 100 times 0.8. I really hope y'all all know what that is before I write it. But I can't pull popsicle sticks when it's a video. Okay. Oop, 20. Remember, these should add up to your N, otherwise you multiplied wrong or something. For Kyle, his N was 70, and the proportion was 0.6, or 60% American manufactured cars. That one I will let you do in the calculator. Won't give you a hard time about it. It is 42. I think it's obvious it's going to be more than 10, but you know. Same thing here. 1 minus 0.6, 28, and those two add up to 70. These are greater than or equal to 10. Whoop, so are these. Cool. So, okay. Sampling distribution of P hat, I'm not going to put P hat 1, P hat N minus P hat K is approximately normal. Cool. Okay. Find the mean of the sampling distribution. It does say show your work, so let's think about how we're going to do that. Remember, we just wrote the formula for mean up here, so we know that mu P hat N minus P hat K should be equal to Pn minus Pk, which was 0.8 and 0.6. Okay, so we expect for the mean of the sampling distribution of the difference between the proportions, the sample proportions, to be 0.2. Find the standard deviation of the sampling distribution, okay? So we know that that has to be, the 10% and random have to be met. They said random samples, so let's just make sure we do make a statement to say that we can assume 1,000 cars in Nathan's state and 700 cars in Kyle's state. And then we'll calculate, right? Seems like a fair assumption, right? That there would be 1,000 cars in one state. Pretty obvious. If you weren't sure, I got these numbers by multiplying by 10, because remember the 10% condition just means that our sample can be no more than 10% the size of the population. So here we're saying as long as the populations are at least this big, then we're safe, and it seems reasonable to assume that they are that big. So since we can assume that, we're going to use this formula for standard deviation that we wrote above. So that would be sigma p hat n minus p hat k, whoop, that's a hat, equals 0.8 times 0.2, that's just p1 times 1 minus p1, over n1, which was 100, right? Oh wait, no, sorry, that's wrong. No, that's right. That's right. Okay, sorry. And if I put this in the calculator, I can say just, sorry if you hear something, it's because my dog is in my lap. Something like that. All right. Any questions? No? Okay, great. You guys are being so quiet today. All right. Hopefully this is in the screen. My little MacGyvered video stand here. Can't really tell, so hopefully y'all can see the top of the page. What are the conditions for calculating a two-sample Z interval for P1 minus P2? Same as they always are, random. Right, they need to come from independent random samples or random assignment in an experiment. Then we have the independence, which is our 10%. Which says that, I'm going to say it this way because it's the way we usually do it. 10 times the sample size is less than or equal to the population size. I think in the book we have it opposite, where we say 1/10 times capital N is greater than or equal to lowercase n. This is the way we do it more often, just like on the previous page with the 700 and 1000. And then large counts. And that's that N1, P1, N1, 1 minus P1, N2, P2, and N2, 1 minus P2 all need to be greater than or equal to 10. One minus P1, sorry. Hopefully that makes enough sense. Each of these needs to be greater than or equal to 10. I think that y'all have that by now. All right, the standard error. Remember, the standard error is the same as the standard deviation formula. We just replace the p's with p hats because a lot of times we don't know the true proportion. And then we'll say p hat 1 minus p hat 2. Y'all get the idea there, right? Now I'll go ahead and fix it. Okay, sorry. Wazzy, be quiet. Okay. So again, this is the same formula as the standard deviation, it's just we're going to put hats on all the p's. So instead of P1 times 1 minus P1, we'll have P1, P hat 1 times 1 minus P hat 1. I'm not going to say this the whole time. And what does it measure? It measures how far your sample proportion difference is will typically vary from the population difference in repeated samples. Sorry if you keep hearing the airplanes. I live by the airport. I hope y'all are okay with me writing sample prop diff. Please don't write that on your tests. But in your notes, it's fine. Okay, what is the formula for a 2-sample Z interval for P1 minus P2? On your formula sheet, there's confidence interval in words. They have confidence interval is equal to statistic plus or minus critical value times the standard deviation of the statistic. For this specific scenario, okay, so still CI, but our confidence interval for P hat 1. I shouldn't have put a hat on that, I'm sorry. The confidence interval is for P1 minus P2. Okay. And that's equal to, okay, so our statistic here is actually going to be P hat 1 minus P hat 2. Our critical value is Z star. Remember, you can get those from the last line in your table B, has the T table, the very bottom line has those. There's also a way to get it in your calculator, and I need to start making sure that I tell you all that too. This is crazy easy to just get from the table. There's some other stuff that it would probably be easier to do in the calculator, but we're going to use a command called inverse norm. It's in the distributions menu. So I'll show you on the example exactly where to find it, but it's, we're going to say inverse norm. So it's the inverse normal. So like you use a p-value to get the z, and that's basically what a critical value is. And the way that we do that for these is we take 1 minus the confidence level, and we divide it by 2 because with confidence intervals, remember, it's kind of like if we have like, oh, just to kind of say, all right, so we know we're going to have tails, right? And so that's where the divided by 2 comes from, because if, say, for example, this is, your C% confidence, then the tails, you would take 1 minus that and divide it by 2. So hopefully that makes sense. And then the other commands, I think these probably just come up in the calculator. We'll look on the example, but the other two that go in there are 0 and 1. This is the way that it's going to appear on your screen in Scratchpad once you do this, but there is a menu that comes up just like on the other stuff we've done where you type it in. I'll show you in a minute. Again, I think for the critical value, it's easier to get it from the formula sheet, or from table B, but anyways, I'm going to show you this. I did it again. 1 minus. Okay, so that's the formula. We're just going to perform this test on the calculator. Like I said, I would like to see you plugging into these formulas in your free response, but I want you to know that if you're not sure that you're plugging in correctly, to just use the calculator. Okay. Example. I can't tell how high I can make this go. Okay. This example is about gun control. This was actually... Remember, we did 10-1 a while ago, or earlier in the week, before the most recent school shooting. So, just by coincidence. Have opinions changed about gun control? Gallup regularly asks random samples of U.S. adults their opinion on a variety of issues. In a poll of 1,011 U.S. adults in January 2013, 38% responded saying that they were, quote, dissatisfied with the nation's gun laws and policies and want them to be stricter. In a similar poll of 1,011 adults in January 2012, only 25% agreed with this same statement. And so, 1 year apart. Explain why we should use a confidence interval to estimate the change in opinion rather than just saying the percentage increased by 13 percentage points. Oh man, really wish that we could talk about this. So, this is just one sample, right? It increased by 13 percentage points for, comparing these two samples year over year. Not even the same people, right? So there is something called sampling variability that I know you've heard of before. And so it's unlikely that our sample difference is exactly the same as the population difference. So I'm going to write something to that effect here. If you can word that more eloquently than I did, then more power to you. Okay. So use the results of these polls to construct and interpret a 90% confidence interval for this change in the proportion of U.S. adults who would agree with the statement about gun laws. So for our state step, we need to define our population parameters. I'm going to use P13 to be, or else it equals, the true proportion of U.S. adults dissatisfied with gun laws in 2013, and I'm going to use P12. And you can name these however you want. This will just help me keep straight which year it is I'm talking about. In 2012. Okay. Okay, you can pretty much see that, right? Just infer that those numbers over there are 2013 and 2012, right? So this is all in my state step. We can say what we're going to do, but it does also say it up there, so I'm just going to write it though. We want to estimate okay. So our plan step. We're going to name the inference procedure that we will be using, which is a two-sample Z interval, or two proportion. 2 samples the interval, 2 proportions the interval. Both are fine. You're going to choose to prop z interval from your menu in the calculator, but just because in the calculator it takes sample, whenever you do the 2 sample, I think it's means. Okay, so both samples are random. Okay, so we can infer from that statement, Gallup regularly asks random samples, that both of the samples in the study are randomly selected. Okay, for 10%, let's see, what was our, it was 1,011. I think it's safe to assume more than 10,000 adults in the United States. We actually don't even need to assume that. We have population data. Right? So we don't even really need to assume there. That's just true. All right, and then large counts for normality. Count, not, okay. So for this, we're going to do all the N1, P1, blah, blah, blah. So, or here we're talking 13 and 12 instead of 1 and 2. But, okay, so N1 is 1, 0, 1, 1. Actually, both the N's are, so times 0.38. That equals 384. I already have this. But you know, just type it in the calculator. You're multiplying. It's not something I need to teach you to do, hopefully. So these are for 2013. And then for 2012, same sample size, and the percentage was 25. Sorry, 1 minus 0.25. And those are greater than or equal to 10. Okay. So we are good on the plan steps. Now do. We're using a confidence interval, so we can plug into that formula we wrote on the previous page. Oh, this is where I was going to show you how to do the inverse norm in the calculator. Okay. So starting out, we know we're going to have p hat 1 minus p hat 2. So here I'm going to do 13 minus 12. That's why I wrote them in that order. Since it has gone up this way, we won't have to deal with as many negatives. Oh, shoot. I didn't mean to do that. This is why we should always use pencil. I just thought pen would show up better for the video. Okay. This is where our critical value goes. If you look at the table for a 90% confidence interval, the table B, it tells you that it's 1.645. But if you want to do that in the calculator, oh, I shouldn't have written this so big. Okay, sorry. If you want to do that in the calculator, it's inverse norm, like what I wrote on the other page. And then here, it's 1 minus 0.9. 1 minus 0.9, which is 0.1 divided by 2, 0, 1. Okay, so I'm going to show you that in the calculator though. Okay, so if you go to menu, is this on the screen? Yeah, statistics. We're going to distributions because we're actually looking at the normal distribution, which is the Z distribution. And then you can see number 3 is inverse normal. That's what inv-norm meant. And so here is where we're going to do, so 1 minus 0.9 is 0.1 divided by 2 is 0.05. And then these two are already there. So that's what I meant by like, just leave them for now. Because on the standard normal, remember that's why we standardize, so that the mean will be 0 and the standard deviation is 1. And then it tells us, so that rounds to 1.645, which is what in the bottom of table B also. So either way. Oh, well, okay, sorry. I should say this is negative. If you remember in the formula, we're doing plus or minus, so it's not going to make a difference whether it's negative or positive in this case. Over here, we'll have our 0.38 times 1 minus 0.38. Feel free to subtract those in your head if you want to. This one's a little easier for me. I know it already. Even though it's Saturday morning, I can remember something like that. And so we can actually calculate this out. We can do this in the calculator, type it all in, hope we don't make any errors whenever we're keying it in, or we can do menu, statistics, go down to 6 for confidence intervals, 2 proportion Z interval, which is 6 again, our successives in the first group. Oh, okay. So we ran into one of these the other day. So they didn't actually tell us how many people responded. They gave us the proportion. But if we multiply, we already did this to check for the greater than or equal to 10. This tells us that 384 people out of the 1,011 in 2013 did respond saying that they were dissatisfied with the gun laws and the wording of the question. So anyway, so we can use that actually as our X. Same thing with the second one. That one was 253. And we're doing a 90% confidence. So I could actually plug this in and figure it out this way, do it twice, one for the plus, one for the minus, but there's so much room for error there. So I think it's probably a good idea to just do the steps we just did. And so I'm just going to pull the lower bound and the upper bound for my interval. Okay. And I'm just going to round because, what's a few thousandths between friends, right? Okay. So that will be our interval. Hey, puppy. Leave me alone. Oh, sorry, guys. My dog wants to get back in my lap. Okay. All right, so conclude. We are 90% confident. Same interval as above. That the interval captures So here's where we have a little bit of leeway of how we want to write this. Sorry, that's a weird R. That says true. I'm just going to use the wording that was given in part B. So the true change in the proportion. Right, from 2012 to 2013 implies that we're doing 2013 minus 2012. But if you wrote that differently, or if you wanted to, sorry, I should have probably said this before I started the example. For any of these examples, I really encourage you to pause the video and try and work through it, and then see if you got it right, especially since this is a section that we've already covered, and you do have a test on Tuesday. So, all right. Based on the interval, is there convincing evidence that opinions about gun control have changed? So whenever we're asked questions like this, we want to refer back to the interval. Since we were taking a difference, we're comparing to 0. If there was no change, then 0 would be in the interval. I mean, you know, at the alpha that we're looking at, but. Sorry, I'm drinking my coffee too. So 0 is not in the interval, right? So that means it does seem like it's changed. It does seem like there's, the change is not 0, which means there is a change. Okay, so yes. And then technically this is, we could figure out at alpha equals, well, it was a 90% confidence interval, which means that alpha would be equal to 0.1, right? Okay, so moving on, let's see. So I have another example here. So again, if you wanted to pause the video and try and work through this example on your own first, I would encourage you to do that. I really hope that you can see this because I really can't see the top of my phone. Okay. All right, so significance tests for the difference in proportions. Hungry children. Researchers designed a survey to compare the proportions of children who come to school without eating breakfast in 2 low-income elementary schools. A simple random sample of 80 students from School 1 found that 19 had not eaten breakfast. At School 2, an SRS of 150 students included 26 who had not eaten breakfast. More than 1,500 students attend each school. So this statement is made here so that we can pass our 10% condition rate. So, what are 2 explanations why the simple random sample from each school do not have the same result? Well, one is that the proportion of the students who don't eat breakfast are actually the same, and we just got different p-hats by chance, right? That's basically what our H null is saying. And then 2 is that the proportion of students who don't eat breakfast are actually different, which is what our HA is going to say. So I'm going to write those in words and also in symbols. So 1, breakfast, not breakfast. Whatever, you get the idea. Breakfast. All right, so all of that, well, that's okay, you get it. H null is going to be our like p hat or p1 equals p2, or that p1 minus p2 equals 0. Sorry, that's really cramped over there, but hopefully you get the idea. Okay, so 2 would be that the proportions are actually different for the two schools. Ran into what I was writing over there. Okay. Right, so this one is going to give us our HA, which would be, we don't have any sort of statement saying that one would be larger than the other, so we're just going to say they're different. So P1 is not equal to P2, or P1 minus P2 is not equal to 0. Those are the same thing, right? Okay, so conditions, they're the same. Okay, we just went over this, okay. Well, I should say P1 minus P2. One. Since that's what we're actually estimating with the confidence interval. Anyways, it's not really what we're talking about right now. Blah, 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 random, 10%, and large counts. Refer back to the other page, though, if you want to see the formulas. Okay, so create a two-way table for hungry children. Okay, so let's see. When we do a two-way table, let's see, so we have breakfast, right? We have two options over here, breakfast and no breakfast. And then we have two options up here, school 1, school 2. And then we can have totals for both, right? At school 1, there were 19 that had not eaten breakfast. Yeah. So 19 that had not eaten breakfast. School 2, 26 who had not eaten breakfast. And that would leave, let's see, so school 1 had 80. 80 minus 19 is 61. So 61 have breakfast, 19 did not. At the other school, there were 150 students, and 150 minus 26 is 124. Okay. So total between the two schools, we had 185 who ate breakfast and 45 who didn't. And that's 230 kids in this hungry children thing here. Okay. All right, so one thing, yeah, never mind. Okay, so the pooled sample proportion is where we take our x's and add them together and our n's and add them together and come up with the proportion that way. We do use this pooled proportion. We don't use the pooling with means. It's just antiquated. You can kind of read there's a little section in the last part of 10.2 if you're curious why we don't use pooled for means, but in proportions we do, but we kind of do it ourselves. Basically, usually if the calculator asks you if you want to pool, your answer is usually going to be no. Can you quit whining at me, please? Okay, so if we want to get our p hat pooled, or our combined p hat, that's x1 plus x2 over n1 plus n2. And we're talking about no breakfast, so we're going to do 19 plus 26 over 80 plus 150. I'm just writing out that step so you see where I'm getting the numbers. Since we already have the two-way table, we've actually already added these up. So 45 out of 230. Okay. Which is about 0.196. Okay. We do this to get a more precise estimate of P. Oh, yeah, sorry. It does ask, why do we do the pool the population? Why do we pool the population proportions? We assume that H null is true, right? Innocent until proven guilty. So we assume H null is true whenever we're performing the test. We just never conclude that H null is true. So we work under that assumption. I know it sounds weird. We work under that assumption, but okay, I'm sorry. I had an alert on my phone and I felt like this was not working. I'm going to go ahead and restart a second video from this point.